Yes, that's the question. Hey, so yes, this is going to be like a bit of a different maybe type of talk. It's more about questions than answers, and I'd like to, especially happy to give it in this for this audience, because I hope I can get people excited to try to think about these questions. Yeah, and it's something that I've been thinking about for a while and try to kind of put my thoughts together for this talk. And I hope it will get you interested. Well, you don't have to drop everything you do and start working on instance-based complexity now. You can wait until after lunch. But so yeah, so what I plan to say is talk a little bit about why do we need the instance-based complexity? What's wrong with either worst case or average case complexity? And most of the talk I'll talk about, if we're trying to define instance-based complexity, what are the kind of axioms we would like to satisfy, and what are the obstacles in trying to do it, and then talk a little bit at the end about how we can make this thing more concrete. And okay, so what's wrong with worst case complexity? So I try to answer this question. I first ask Google. When you write what's wrong with, that's what, maybe it's because I did do incognito mode, so to try not to make it tailored to me, but because maybe I was in Boston, that's why it says what's wrong with the Red Sox, with the Celtics. And then you add worst case, then it all, like plenty of people apparently think that there are things that are, I think apart from diabetes and depression, it seems like people are mostly worried about worst case analysis of algorithms. Okay, so what's wrong with worst case? Why do people don't like worst case complexity so much? So I think we really want to separate worst case algorithms, upper bounds, and worst case hardness results, lower bounds. So generally, people are pretty happy when you have a worst case upper bound. If you can, give an algorithm that can sort a list of integers in n log n time, or solve the minimum cut problem or the two-sat problem, that's very good. It's all the foundations of computer science, basically in the 50s and 60s, were about algorithms and data structures where we have worst case guarantees on all possible inputs, and that has led to amazing theory, etc. And people are less happy when you have worst case hardness result, like NP hardness. If instead of min cut you talk about max cut, instead of 2-sat you talk about 3-sat, then people are not so happy with these results. Not just because obviously it's always better to do something than not be able to do it, but also because people say maybe this is not as meaningful as the easiness result. And there are some criticisms that people put forward which I actually don't particularly agree with. So let me start with them. So some people say, these results are meaningless because if you look at SAT solvers, they show that P equals NP in practice. And I don't really think that's the case. For every one of those SAT solvers, it's very easy to produce inputs, and there are actually very interesting inputs on which it chokes. And there is a reason why you have SAT solving competitions and you don't have sorting algorithms competitions. Because if it was so easy to solve it, if it was so easy to solve SAT in practice, then they wouldn't need to have competitions, right? And another thing is that maybe they say, well, machine learning, when you're doing machine learning, you're doing deep learning, you routinely solve NP hard problems. And again, this is not completely accurate. You really, when you're doing machine learning, you typically try to find some classifier that minimizes, maximizes performance on your training set, and a lot of the time you're phrasing this as some kind of an NP-hard non-convex optimization problem, but it's not really the problem you're trying to solve. In fact, if someone gave you a solution for this problem, that the only thing was guaranteed about it that it was a solution, often it would not be good it would not be actually what you're really interested. And the whole thing in machine learning is usually, most of the time you're doing it for artificial intelligence, which means that this is just one component in performing a task which humans already know how to do anyway. So just as we don't think that because a human can distinguish a cat from a dog, that means that they solve NP-hard problems, then no reason to think that because we can design an algorithm that distinguishes a cat from a dog, we also solve NP-hard problems. So those are not the reason I think valid attacks on Worstcase, but there is something to that, and the way I view it is the following. So if you look at the Worstcase algorithm, in some sense what it says is the following. I can take say the instances of two satisfiability, and I can take the ones where the answer is yes and the answer is no, and I can find this efficient algorithm, a very kind of simple way to classify and distinguish between the ones where the answer is no and the ones where the answer is yes. So it says something about the structure of this problem, and something very, very powerful about the structure of this two-sat problem, that you have this way to kind of, if you identify the efficient algorithm with linear kind of in some space, after you can embed it in some space where after some space you can basically put this kind of line, a plane, where on this side there are the no instances and this side are the yes instances. But if you think about what does the worst case hardness result for 3-sat means, it's harder to interpret it. It's not clear whether maybe it means that it looks something like this, like you would never be able to separate out the yes and the no matter what you try. Or maybe it means it more looks like something like this. Like maybe it's almost separable, but there is just like a small obstacle that makes it makes it impossible for us to distinguish yes and no. But in some sense, if that was the true picture, then maybe 3-sat would look much more like 2-sat, and in this, if this is the picture, then it would look kind of something completely different. And the mere fact that 3-sat, say, assume we take P different from NP as an axiom, the mere fact that 3-sat does not have a polynomial time algorithm doesn't help us distinguish between these two scenarios. And in general, people sometimes say, you look at an NP-hard problem, and maybe you find like a subset of it, maybe for planar graphs or for some other or for some bounded tree reads, for something like that. You find like islands of tractability. But a priori, we don't know if it's really about islands of tractability or about islands of hardness. We don't know if the problem should be we should think of an instance as being hard unless it's proven otherwise, or so unless it has some special structure, it will be hard, or maybe it's the opposite. Unless it has some special structure, it will be easy. And NP hardness or worst case complex hardness by itself doesn't tell us a way to distinguish between these two things. And there is so there is a reason why people have passed to average case complexity. But in average case complexity, it's a little bit like a mirror image. We are happier actually in average case when we have hardness results. So hardness results in average case complexity are very useful. We can build crypto primitives out of them. We can maybe show also barriers for learning problems. And actually, algorithms for average case complexity tend to be not so helpful again, if you take them as a black box. Because often if you fix the average case distribution, you can often tailor like a very silly algorithm. Like for example, planted click is is generally a hard problem, but more or less in the regime where you have nice spectral algorithms that work, also some silly algorithm which basically just counts the degrees and would also work as well. So often it's not very interesting if you tell me that an algorithm works. If you tell me that you have managed, right, if you tell me that you have managed to come up with a sorting algorithm that sorts in O of n log n time, I'm very happy. If you tell me that you have come up with a multiplication algorithm that multiplies two integers with O of n log n times, I'm very happy. So worst case upper bounds algorithms are very interesting as a black box. You just tell me the result, I say, okay, it's very interesting. If you tell me that you came up with an average case algorithm for a problem which, say, maybe the fact that the algorithm works on the average case a priori doesn't mean that it's a good algorithm to use in any particular setting. What you really want in average case analysis when you're talking about upper bounds is to show that you have some natural algorithms that works for many different distributions. and then that's kind of a useful, positive thing to say about the algorithm. For it's like we're very happy with say smooth analysis result for the simplex, because also we know that the simplex is a good algorithm. It would be much less interesting to the existence of an algorithm that has a similar performance. So in average case complexity also we are not super happy, because given a very particular input distribution, it's not so. So I'd like to do something in kind of the middle. And another thing that we are not happy with average case even hardness is that generally, even when we want to prove the hardness results in average case complexity, we don't have the equivalent of P different from NP. For every average case hardness results could be very useful, but generally we don't have any algorithm or any factory to make them. We don't. We basically every time someone in the crypto community, every time they need a new average case hardness result, they make a new average case assumption, and we don't even have reductions between things like random 3-sat and random 4-sat or things like that. You would think that they would be basically the same, but we don't really know how to show
we have the Levin theory, which is
yeah, on non yeah. So you either give up on natural problems or natural distribution input distribution. But if you have like a specific natural distribution and a problem, then or two of them, you usually don't know how to relate the two. And then so that's. Yeah, and even though kind of intuitively we do think they have a similar difficulty, but we just don't know how to kind of relate them. So there is another perspective why you might say that instance-based complexity makes sense. That if you think of these problems that we study in theoretical computer science, for example, think of max-cut, you can write it as some maximizing over a Boolean string of the sum of this degree 2 polynomial that says 1 if the edge is cut and 0 if the edge is not cut. If you think of 3-sat, you can think of it as maximizing some degree 3 polynomial in the following sense. If you think of Hamiltonian cycle, you can think of it as maximizing the dot product of G with the matrix that corresponds to the edges in the cycle, and there are some polynomial constraints, low degree polynomial constraints that would say that this is a cycle in which every vertex is connected to every vertex, and in fact you could even put these constraints down there, like say just put it as a penalty function. So you can again think of Hamiltonian cycle as just maximizing some low degree polynomial over the Boolean cube. And of course also the easy problems, minimum cut also as well. And in some sense, all of the 21 car problems and many other problems, you can think of them as just instances of this problem, maximizing P of x, where P is low degree polynomial, over the Boolean cube. And of course, this is an NP-hard problem, so maybe it's not a very meaningful statement, but for most of these 21 car problems, except maybe subset sum that has integer arithmetic, the reduction is very kind of natural. It's not like you. So you really can think of them as basically just. So rather than thinking of them as problems, you can think of them as a class of instances. So in some sense, we have already been doing instance-based complexity. So you can think that you have this meta problem of maximizing polynomial over the cube, and then you have some classes of instances. So min cut is a nice class of instance where it's partitioned nicely, and 2-sat is a nice class of instances which also.
The instance is a polynomial.
The instance is a class of polynomials, like the min-cut polynomials are polynomials that are induced by a graph, and yes. So the instance is a family of polynomials, and there is the min-cut polynomials, the 2-sat polynomials, and then the max-cut, and well, this theory, the upper bounds tell us something very nice about what it looks like in these boxes. It doesn't tell us a lot about what it, what Karp's result basically tell us that this is not going to look like this. But aside from that, it doesn't tell us a lot. In some sense, if you have, like, say, your instances, for example, if they fall outside, as actually it's often the case in these machine learning things, they just fall outside of any one of those nice boxes, then the theory doesn't tell you anything. In some sense, even if it falls inside these max boxes, the theory doesn't tell you anything, because you're trying to solve like some set of max cut instances here. You have no idea if this is going to be hard or easy, because all the theory tells you that there is no partition like that for maxcut, but it doesn't tell you that there is no going to be a partition like that if you restrict your attention inside this ball, which you haven't really completely, very hard often to completely classify.
So you didn't say what instance-based complexity. I mean, it's the same problems you talked about earlier.
Yes, so I didn't yet define what is instance-based complexity. So, so basically so first of all, what are instances? So for most of this talk, basically think of instances, there is going to be some abstract map, mapping an instance I to the value of I.
So instance is like the graph in the Hamilton.
The graph, yes, yes.
So the fact that it's encoded by a polynomial is
right.
Just a convenient framework you like, but
yeah, but
the graph. The instance is a normal instance.
Yes, you can think of it as a graph, or you can think of it as a polynomial. It's equivalent ways to. So generally, most of the time, I will just talk about the instance. There is a number attached to it, like there is a map maps I to val I, and usually, often I'll think of, say, the instance as being some low degree polynomial, and the value will be the maximum of this polynomial. But you can think of other cases. In this case, the search problem is in some sense to find an X that shows that the maximum is at least some number tau. The refutation problem is the task of certifying that the value is at most tau. And you can also talk about just the computation, just compute the value of this polynomial. And why do low degree polynomials arise so often, say in 21 car problems, etc.? And one theory it could be is that often the way things work is that you run your instances really come from something from the real world which you measured, and every time you measure something from the real world, you might have some noise added to this measurement, and therefore very high degree. If you're trying to kind of optimize very high degree things, more often at the time it will not make sense because there will not be meaningful statistics of your instance because it had potential noise. So that might be like one reason why we often end up looking at low degree polynomials. But
anyway. We also end up there because 3SAT is empty.
Yes,
so 3SAT. We can reduce.
We can reduce. But I guess the point I want to make is that usually the reductions are not very unnatural. Like, so say if you look at the most canonical problems that people study in combinatorial optimization, often, things that are not determinant or permanent, often the natural way to express them is by a low degree polynomial.
Permanent determinant are very natural.
Yes.
Also, circuit value is very natural.
Yes.
And it's not a low degree.
Yes. So there are so there are examples like that, but most, I think, or many, and this is kind of what I'm trying to. When we move past abstract this discussion, I will try to think of mostly of these kind of things. And and you can also think, and I'll put it in gray because I'll not focus on this talk so much, but I think actually maybe it's quite possible that eventually the theory will be cleaner if you actually talk about more like sampling and problems where the value rather than the maximum is kind of like a partition function, like a sum. You sum e to the polynomial for some that might actually end up being in some sense a cleaner theory, but I'll ignore that for now. And typically we'll also think of noisy version of P, and we also only want to approximate these values within plus minus epsilon. So, and part of these ways to think of it as low degree, add noise, etc., is to kill permanent and determinant. So I want to rule them out of the theory. So what do we want from instance-based complexity? So generally we want a map that takes an instance and gives a real number which corresponds to its complexity. And the way I think about the C of I would be kind of the exponent, like n to the C of I should be the running time to solve the instance I. And completeness, first of all, we want some algorithm that does solve I in n to the C of I time. And soundness, and this is the thing we'll talk about more, so there is an asterisk. This is not going defining exactly what we mean here will be a problem. I want to say that no algorithm can solve I in less than that, in n to the little o of C of I time. So that's ideally, like if we could do that, then we would basically have like an instance-based complexity theory. But in some sense, I would like even, again, this part will obviously be conjectural because we typically don't have, without P different from NP, we don't know how to prove any hardness. And also there is another thing that I would like is I'd like this map to be useful in the sense that I would like not to be like a Kolmogorov complexity where the Ci is a number that is defined, but no one can ever tell what it means. I'd like to be able to have a number that is actually computable and that I can actually analytically estimate for some classes, say, given a set of instances. At least I have a fighting chance in estimating what is the maximum complexity or what is the expected complexity over this set of instances. So I'd like to be have a very kind of concrete measure rather than something very, very abstract. Yes?
Sorry, I'm getting a bit confused. Like, so an instance is a class of instances?
No, just one instance, one graph.
Like, but for a one graph, I mean, I can always store the output and just...
Yes, that's why there is an asterisk. That's why there are obstacles. So that's exactly the problem. That why this question, why this talk is actually, can there be an if theory, and why it's not like trivial to come up with a theory like that. So it's not trivial to for worst case complexity, etc. It's very there is a very natural way to define what it means the complexity. But here, because you enumerate over all algorithms, but here it's a little bit more, in some sense what I would like, yes, to draw kind of a heat map. This is obviously not going to look like that. This is some image I download for Google Images, but some kind of a thing where you basically would say, here is the complexity of every instance, and then, 2SAT is easy because all of the instances are like in the things with small complexity, and maybe MaxCat is hard because it has like some intersection with the high complexity vision, etc. And really do this thing which, as you say, it's problematic. Assign a time complexity for every particular graph. So, and I think, in fact, if we're already doing impossible thing, I'd like to do even more. I'd like to also talk about the computation and knowledge. So not just talk about the running time to solve the problem, also try to quantify what do time-bounded agents know about the problem. So for example, what the error bars do they have about the optimal value, even if they cannot solve it completely? Again, for that particular instance, if they had to say they're given some SAT formula, and now they want to, and it has some satisfying assignment, but they want to kind of quantify the posterior distribution of the uniform distribution of a dissatisfying assignment. So if you think about it like in statistical physics, they are given some system, and they want to talk about the distribution, the distribution that kind of corresponds to all the states of the system in a given temperature. So they would like to basically take computational estimates for the entropy of this distribution, computational estimates for all sorts of marginals. Even though they might not be able to sample from this distribution, it might be hard. I would like to say, to quantify how hard is it. So they don't get the correct marginals, but how incorrect are they? They don't get the right entropy, but how bad do they get? So in particular, what I would like from a theory like that is that if you're able to compute this, then you would take, say, parameterized distribution. Like, for example, think of 3SAT, random 3SAT, where you have like alpha n clauses. And you would be able to, say, maybe draw a figure like that, which would predict the running time. Often it seems that this running time jumps from polynomial to exponential, that as a value of alpha, it will tell you when it jumps from polynomial to exponential, the time to solve it. And I'd like to do more. So for example, if you look at the entropy of solutions for a 3SAT instance, then it looks a little bit like this. There is a point which the entropy jumps down to 0. It's no longer satisfiable. And then I'd like to look at what are the computational upper bound. So it seems that at some regime we are able to basically solve the problem and sample from the distribution, so our computational upper bound is tight. And at some point it's possible in 3SAT, seems even more possible in KSAT for larger K or for some other problems, that there is a gap where we are not able to sample from this distribution of the actual solutions. So you can think of it that there is a gap between the entropy, the true entropy, and the computational entropy, and then you can think of it, and then you can think here, for example, there is the true entropy is 0, but we don't know how to refute. So the computational entropy is non-zero. And
we don't know how to prove that the formula is unsatisfactory.
yes, we don't know how to prove that
Efficiently prove it.
yes, so in some sense you can think that the computational entropy is non-zero even though the true entropy is 0. And similarly, you can also ask about computational low bounds for the entropy. So I would, a theory of instance-based complexity maybe would give principled way to draw these graphs, which, you know, physicists sometimes draw not exactly these graphs, but something similar, but sometimes they don't really have a principled way. Sometimes they change their mind after, like, you know, they have like some intuition that it should look like this, and they said, okay, actually, maybe we missed that structure, and maybe the threshold here is not here but there. But so it's not like there is like a very principled way to do it. And yeah, so you would like to get like these algorithmic threshold. You would like in machine learning to get sample trade-offs between the number of samples you need to observe and the computational time. You can have this intuitive idea that sometimes you need to trade off the two. Maybe if you could solve P versus NP, you could do these things with 500 samples, and maybe now they still solve it, but they use 5 million samples, and you can ask what are these kind of trade-offs.
But still, you want this for any algorithm.
For any algorithm, yes.
You want the theory to work for every algorithm.
Yes. You want a theory that really predicts computational hardness, not yes.
Not for particular type.
Yes.
Of algorithm.
Yes. So yeah, and why?
Just in proof complexity, you have sort
Right.
of instance-based complexity for families.
For families of proofs.
Proofs or algorithms.
Right, and in some sense, you could hope that maybe some that could be useful. Yes. So why you could even hope for something like that? So one reason is that if you look at these problems, even though you have like all of these kind of different problems, like you have graph coloring, and you have 2-SAT, and you have 3-SAT, and you have TSP, etc. All of them, they seem to the same kind of algorithmic ideas seem to be repeating. And often you see the same thing. You see, linear and semi-definite programming. You see local search. You see, for sampling problems, Monte Carlo Markov chains, or like the message passing algorithm, like belief propagation. So it seems like the space of problems is much richer than the space of algorithmic ideas that we apply to them. So
you will mention Ragaventra, or you want to mention it now?
Ragaventra is like some hope for at least for algorithm optimality in the worst case version. So there is sometimes there is formal evidence that for some classes of problems in the worst case setting, at least you do have one algorithm that is the optimal one. And so that's definitely one. Yeah, that's a good. That's definitely some indication that something like that could potentially be true. And in general, my sense is that if you my sense is that you could look for this. The metaphor I like to sometimes use is I want to do the theory like it's like this drunk that lost a coin and then looks for it under the street light. Rather than looking for it where they lost it, because it's easier to look for under the street light. So my way is I would like to have the theory for the problems that are under the street light, and the problem which are actually very interesting. So the problems that to me that are under the street lights are problems with combinatorial optimization, where there seem to be much more uniformity in sense of like we use the same ideas time and again. It seems to be like much less, very clever algebraic tricks like you do with, factoring or other problems like that. Algebraic problems. There seem to be even cleaner theory in the sense that in combinatorial optimization, it seems like effectively P equals NP intersect co-NP, even though in general we believe this is false. But in the context of combinatorial optimization, often that's actually historically how it was. Like people came up with duality, a certificate for that something is certificates that say the objective value is at most something, and that led to an actual algorithm. I once gave a talk in Cornell, and then I said something similar to this, and then after that, David Schmois came to me and said, now I know that I really work in combinatorial optimization because I really believe that P equals NP intersect co-NP. So apparently you can have a very long career in combinatorial optimization and never encounter a problem that causes you to not to think like that. While if you you cannot finish an intro course in cryptography without encountering a problem that causes you to like lattice problems or integer factoring, etc., that causes you to think that P is different from NP intersect NP. And there are also these kind of hints from the statistical physics that these kind of structures of that these some certain average case problems undergo phase transitions, which could be potentially related to their computation complexity. So these might raise hope that there could be a theory like that we would that's out there to be discovered. So okay, so now I'd like to talk about obstacles, which some of you already talked. So this is what we want, and why we cannot get this exactly, and what we could potentially hope to get. So one obstacle is this kind of stopped clock paradox, that even a constant stopped clock is right after time, and similarly, if the value is either 0 and 1, then the constant time algorithm that just outputs 0 will work half the time, and if the value is between 0 and 1, it will work epsilon fraction. You will get accuracy up to epsilon fraction of the time. So you can have a trivial algorithm that already works for half your instances or constant fraction of them. And one solution for that is we say, okay, we'll do algorithms with error bars. So for example, we will restrict to algorithms that certify that the value is at least tau. One way to think about it is we think of the search problem. The algorithm doesn't just tell you, yes, the formula is satisfiable, it also spits out a satisfying assignment. So at least that solves this problem. And sometimes I would use the proof complexity notation because this algorithm certifies that the value is at least tau. So sometimes I'll write this algorithm certifies in time t that the value is at least tau.
So you sort of assume that we have something in sort of NP intersect NP, only that it's not P, that the time is not polynomial, but
possibly
some time for certifying positive instances, some time for...
Right, so right now I'm focusing, say, on positive instances, so right now it's maybe just NP, but so I just want to restrict to algorithms that also spit out an assignment. The reason I'm trying to talk about more generally, because maybe at some point I'll think of this value as, yes, like upper bounds, lower bounds, sampling, etc. But right now, let's just keep in mind, like, just outputs a satisfying assignment, or nearly satisfying assignment. And at least that kind of takes care of this problem. And now we kind of modify our goal. So now we'll say our time instance complexity measure will also take some tau. And given an instance and a value tau, it asks what's the minimum number of time to take to certify that the value is at least tau. If the true value is not at least tau, then this will be infinite. So now this is now updated definition. We want this thing that we can certify that the value is at least tau in this c tau I time. And so the way we will write it is that we will write it that we have some kind of a canonical algorithm that comes from this completeness condition or proof system, you can think of it. And basically c tau I will be the minimum log of the time that it takes to certify. So you can think of it as the length of the proof, or it's a time to produce it.
But yes. You're doing it over all possible algorithms, or I don't quite understand.
Right, so the completeness condition says that there exists an algorithm. So this is the completeness condition. So there should be, we want some kind of a definition which will come up with some canonical algorithm. And now we'll define it for this algorithm. But we want the soundness condition would be that there is no better algorithm. And we still haven't figured past all that.
How would you know there's no better algorithm?
Well, how do you know that P is different from NP? You would have to conjecture that. Yes, the soundness will have to be conjectural, but we want to see if there is even a way to make a conjecture that doesn't, fall apart after, in the next slide. And for that, we have to worry a little bit. And so you can formally say you would like something like that, right? That if the algorithm certifies that the value is at least tau, then the t must be at least n to the omega, at worst polynomially slower than this thing. And again, we still like it to be useful definition. And there is a way to define this, but I don't like it because of the usefulness. So you could use Levin's universal search. So this is like a long math way to say it, but annoying way to say it. But basically, you can define the algorithm that enumerates over all Turing machines, runs them, tries to spit out a satisfying assignment, and if it does so, it outputs. So that will be a definition that will satisfy my soundness and completeness conditions, because it just enumerates over all Turing machines. But I want to rule this out as a solution, because I will never be able to, it just kind of pushes the problem aside to another side. I will never be able to analytically analyze. It's kind of inherently non-effective, and it cannot handle non-uniform algorithms. So in particular, I would like to even handle non-uniform algorithms,
What's non-uniform?
Circuit. So I'd like to also, in the soundness condition, in the completeness condition, I'd like a single uniform algorithm. But in the soundness condition, I would like to also be against all circuits.
But still this issue of hard coding.
Yes. So now we have this hardwiring. Every instance has a linear size circuit, because for every NP problem, you have a circuit that of size n that just spits out the assignment for it. So now, in some sense, now we've made our problem even worse in some sense. And it gets even worse than that. Like, this is even not, it gets even worse like that, because you have symmetry and noise. So it's not just one instance. Basically, suppose you hardwire you think of a graph problem like MaxCut or something like that, and you hardwire a single graph for which this algorithm kind of knows that the value is at least tau or something like that. You can then have basically n factorial graphs obtained by applying some automorphism to this graph. So now it's not just one instance, it's n factorial instances. And you can add, epsilon, if your graph has like m edges, you can add like epsilon m edges. And so add like an exponential in, another, all sorts of graph, basically like G0 plus noise, where you also know that the value is at least tau minus epsilon. So basically by just hardwiring a single graph, you get a whole family of, by symmetry and noise, you get a whole family of graphs that, if there is just one graph for which your, say, canonical algorithm fails, now I can give you like a circuit that will, beat it on exponential number of, on exponential number of instances. So how do we try to fight it? So the approach I'd like to propose for defining like instance-based complexity is a little bit like how we define a probability for infinite spaces, like using density functions. So we want to define complexity per instance, even though for every particular instance there is a linear size circuit. And this is not a great analogy, but it's some analogy. It's like we want to define a probability density function for, for a point in the unit interval or in the space R, even though the probability of this point is 0. And what do we do? Like the way people do that in probability theory, in measure theory, is that they say, okay, we define this probability density function, but it's only meaningful if you integrate it over a measurable set. So you define this thing, but it's not, but you cannot directly apply it unless you integrate it over a measurable set. And similarly, what we'd say is we'll define it per instance, but we will only be able to derive some meaningful results from it if we integrate it over good distributions over instances. And now we have pushed all the problem into defining what is good, which we'll talk about. But this would be the idea, that you define, that at least in principle, it's possible to define per complexity number, which would still be predictive of the performance of algorithms over any good distribution.
People have tried to define families of good distributions
right.
In Averagecase complexity.
Yes.
Through the decades of various, where an adversary can decide some of the,
yes.
Maybe there's a distribution, then an adversary perturbs it, and nevertheless. So how general?
Right. So one of the things, one of the problems that, for example, that usually in average case distribution is that that in average case there is a base measure. Like so, for example, if your base measure is g and half, even if you allow adversary perturbation and all that, it will never capture random graphs of degree 5. So I would like a measure, I would like
There are other things that are proposed, where you don't fix any distribution a priori, but you allow, you ask the instances to have some structural property, like the value of their optimal solution doesn't change if you perturb epsilon fraction of the edges. So
yes, so those could be like,
that would be good.
Yeah, those might be, but definitely what I would like to say is that, for example, if I look at about distributions over graphs, so now I'll talk what about the desiderata, like what do I want from a good distribution, but definitely I would like to say that, say, random graphs of every degree are good, that's at the very least, but somehow the definition should not be tailored to that. So and I like something that makes sense for a very abstract kind of notion of instances. So okay, so now what I would like is the following. So I like this completeness condition, and I would like that for every good distribution, if A succeeds on this distribution, then with high probability, if it runs in time n to the k, or the size of it as a circuit is n to the k, the complexity is O of k. My instance-based complexity measure is O of k. And the way I write this, not so important thing for this talk, but the way I write succeeds, it means, say, certifies a value of at least tau plus epsilon. Let me give some epsilon slack to make it a little easier.
So again, maybe you wrote it in the contrapositive, now the soundness condition.
Yes.
You want to repeat it?
Okay, so I'll repeat it. So yeah, so the one way to say it, I can write it also in the different ways. I can say, if you have a distribution such that with 99% of it, the value of the complexity measure is at least k, you will not have a circuit of size n to the little o of k that solves it with high success over this distribution, or in the contrapositive, if you have a circuit that succeeds with high probability over this distribution, then the measure should also be with high probability at least at most O of k. And it's not the same about as average case complexity, because we do want this for all quantifiers on all good distributions. And the main thing is, if our notion of good distribution is only the uniform distribution is good, then it is the same as average case complexity. So what do we want from good distribution? So one thing is we would like it to be rich enough to capture a lot of average case complexity problems that people have looked at. So, for example, you want like random noisy constraint satisfaction problems in all densities, planted clique and denser subgraphs in all degrees, tensor decomposition, there is sparse PCA, you want to certify a restricted isometry property of showing all sorts of springless models from statistical physics, etc. So you'd like a notion of good that is rich enough to capture a large class of problems that people have looked at. So, and but on the other hand, you want it to be restricted enough to avoid certain obstacles. So in particular, it needs to avoid this idea like instances that you get by taking a single instance or a small list of instances and just say applying some symmetry to it that doesn't change the value of the problem, like permutation in case of graphs, or maybe it could be in case of CSPs, and adding some noise. And another thing that's more subtle, but if you want a chance at a clean theory, you'd better get that also, is you want to avoid something that could be output from a reduction of from factoring or something like that, because we really want to look under the streetlight. If we don't want to start trying to claim that our algorithm discovered the number field sieve or anything like that. So we cannot. So we really need to somehow rule out algebraic structure in. So ensure our notion of goodness. So we really want to say. So in some sense, this could also basically be captured by that. You just want more balls than what you would think otherwise. And you kind of want to say you cannot be covered by a few balls and equivalence classes. So and one of the things that somehow you have to kind of be careful about is that, say, if you look at say the random graphs of degree 3, we would like that to be good. If you look at a single graph of degree n over 10, and you apply a random permutation to it and noise to it, this distribution has much more entropy than random graphs of degree 3. So your definition of goodness cannot be everything that has sufficient entropy is good, because you would have like a lot of distributions that are good and have very little entropy, and a lot of distributions that are bad and have a lot of entropy. So it's not just kind of, let's say, we just replace uniform distribution with high enough entropy distribution and call it a day. And we also want to, to be simple enough so that we can actually prove that a distribution is good unconditionally. We don't want that there to have to use a conjecture, and we want to be able to analyze it. So what we would like to be able to do is, once we have, say, found a distribution of good, we make the single conjecture that our complexity measure is sound, and from that conjecture, we ought to be able to get like all of those average case problems, like figure out for all of them, at least in principle, having kind of a finite computable way to, at least in principle, it might be very, very complicated to carry it out in every particular instance, but having a finite way to figure out the thresholds in all of those average case problems and without making any extra assumptions. So in particular for crypto, you make this one assumption, now you derive all, you don't make the same, you don't need to make an extra assumption every time you come up with a new problem. And now I don't have yet a very candidate definition that I can 100% stand behind, but I have like two classes of proto definitions, and so I wanted to kind of display both and talk about some of the trade-offs. So there is one which is somewhat, I'll call it, both of them are somewhat radical, because you assume that one algorithm is optimal for all possible, good distributions. So both of them are radical, but one of them is even more radical than the other. So, so one of the more mildly radical is something that somewhat implicitly has been in several works. I think the only person I know that really put it out, like in writing, is Sam Hopkins in his PhD thesis, which basically says something. So he says, let's define a class of clean, simple generative models, and then say these sorry, good. I keep changing the adjective. At some point I thought maybe clean, and now it's good. I don't know what's the right thing. So good. So it's good if it comes from this model, and the more radical thing it would be.
For the mind. I mean, since instances could be, clauses in formula or,
yes.
Or graphs or
yes.
very different things. So the generative model.
It's family of models. Yes, so it's a family.
But it's maybe. But you sort of implicitly restrict yourself to CSPs.
No, because you definitely no, because
it would be good for graphs, also for graph isomorphism problem.
So I would hope to, like, with this philosophy of adding, breaking the algebraic structure, I would hope that graph isomorphism, this should be fine for like noisy versions of graph isomorphism, but not the actual graph isomorphism. Hopefully, you'll have enough noise to kill the group theory. So this should capture kind of the intuition that graph isomorphism is often easy on average without needing to go full bye-bye on it. And the more radical definition, which again would be interesting, maybe more as to rule out and really explode this space, as maybe to actually believe and stand behind, is that all distributions are good unless kind of proven otherwise. Unless they have unless they meet a very specific obstacle that causes them to be bad, they must be good. And in some sense, the way I would think about it, it's a little bit related to questions that Moni Naor and Danny Harnick asked a while ago, and then Andrew Wacker also worked on of instance compression. So in some sense, the general distributions are one that can be compressed in some sense to a small number of equivalence classes plus noise. And okay, so let me talk about the less radical definition, which maybe is cleaner a little bit, or good or clean. I keep changing. So the idea is basically you'd say, what is a good? You have a generative model. You apply some generator and to the that gets coins, and then you add also some noise.
The generator is just an efficient algorithm that has a random input.
Right, but now we want to restrict it, and the way we'll restrict it, we'll say that the generator is a degree is a constant degree polynomial, and it will also have to satisfy symmetries, and a lot of symmetries. And I don't know yet what's the right definition of symmetries. Definitely, like but definitely you want enough symmetries. Say maybe this should be SLN. So you want it to be symmetric under a group, which is rich enough. For example, symmetric under all permutations, or maybe symmetric like if this polynomial, say, outputs a graph. So it's not like permutation over all edges, but permutations over vertices. It outputs a tensor. It might be permutations over, along every axis. And it might be a matrix polynomial. So, you want to say it's permutation along, invertible transformation. But the idea is that it's rich enough so that this polynomial, even though there is one of them per n, it is actually defined only by a constant number of parameters. So, if, for example, symmetric polynomial of degree d, you only need to specify how you only need d numbers to specify it for every value of n, because it's always a linear combination of the elementary symmetric functions. So you want the model to be such that every model like that should be specified by a constant number of real numbers. So you'll only have like these real numbers which define this product measure, and let's think of it as either something that's either like uniform over some finite set or a Gaussian, or like a p-biased distribution. Possibly the p could be n to the minus delta for delta, which is a number. But basically, any model like that should be defined by only a constant number of real parameters. And the hope is that every model like that would be nice. In some sense, Hopkins gave a more restricted definition that captures some such models, and for which at least he couldn't think of a counterexamples of an example. Yes?
What is the concern? The concern is that you define some hardness measure,
Mm-hmm.
and then there is a distribution that's kind of natural, where the measure says that it's usually hard, but the problem is actually easy.
Right, or that you define, there are two different types of concerns. So you could define these too restricted and rule out a lot of problems that people care about. So you could define, your notion of what is a good distribution too restrictive, and then you rule out a lot of what a lot of people care about. Or you can maybe define it too rich, and suddenly you're able to say, take an instance of factoring, apply a reduction to it and a PCP reduction, and suddenly you get a low degree polynomial where approximating this polynomial is equivalent to the factoring problem, and you find yourself basically claiming that your reduction kind of boils down to whether 2 to the n to the 1/3 is really like the best thing you could do, you kind of end up being very, like, whether your notion is sound or not, end up depending on very deep questions in algebraic. We have no way of knowing. And so you want your measure to be rich enough so it captures a lot of problems we care about, and poor enough so that it doesn't allow you to embed in it very structured problems for which we know of very tailored algorithms.
So why doesn't it capture your definition of taking a graph and then permuting it?
No,
Possible ways. Is it a good distribution or a bad distribution?
No, this would be a bad distribution, because to hardwire these graphs, you would need really n parameters for every. We don't know a way to generate, I think, hard graphs. So this maybe the right way to think about it. What's I hope. Okay, they haven't proven it, but I hope, for example, that the following will not be a good distribution, which is for every n, take the first n squared digits of pi, use that as your base graph. Now the distribution is permute that and add noise to that, or something like that. And I hope you could not write the algorithm which extracts the nth digit of pi as a low degree polynomial of this form. So at least I don't think you can do that. So that would be like the reason why. So these are supposed to be. So think, for example, the simplest case is think of a polynomial that's really permutation invariant. So then, but usually, or maybe what we'll think of is not really all permutations, but say you output a graph, but it needs to, but your distribution. But and your polynomial, your generative model is really just defined. If it's degree d polynomial, it's all really just defined by d numbers, which is or d whatever.
The degree d polynomial that is a generator is a multivariate polynomial.
Multivariate polynomial, yes, but it has all the it has n to the d coefficients, but because it has to have satisfy all these symmetries, it can be spanned as a like a more restricted. It can be spanned as a more restricted. At least that's the. I do believe this is the case, right? If okay, definitely for permutations like degree d. The polynomials that are invariant other permutations, degree d, the number of generators for them is only d.
Yeah, but if you take permutations over the vertices of the graph,
yes.
then the graphs can have difference.
So that, so now I have to think. How many of those are there? Yes.
I don't think
it's not a constant depending only on d. So yeah, so we do have to somehow restrict maybe even further because we want polynomials that are somewhat natural in the sense that they only are determined by a fixed number of parameters for every n. And let me give you kind of examples. Like for example, for all of these problems, you can think of like fairly simple polynomials that random tensors. Then the polynomial takes our vectors, just outputs the tensor that this is the rank decomposition. Implanted click.
Sorry, I don't understand this example. What are the constant number of parameters?
So the constant number of parameters is not the number of inputs, but rather the number of maybe the way I can define I can write this polynomial as a very simple function, in the sense of I can write this polynomial as a very simple function of its inputs, and it has all these symmetries that basically no matter how you no matter what you apply, like any rotation you apply to each one of those coordinates, or any permutation you apply to this, so those are the symmetries that this polynomial satisfies.
But the number of parameters is r times n, it's not r.
The number of inputs, the randomness is r times n. What I hope is that this class of symmetric polynomials is such that I can describe this polynomial. Obviously, I can kind of describe this polynomial in number of symbols that is. So I hope that there is a description. I was pretty sure of it, but now I have to now check. Maybe we should talk a little bit more about this invariance.
But maybe it's only me who doesn't understand. I mean,
yes.
In these examples,
yes.
What can you tell us in some of them? What are the constant number of parameters and what these parameters are?
Okay, so yeah, that's a very good question. Now, okay, so in these examples, typically the way I would think about it is that there's two kinds of parameters. Like for example, let's look at say planted click problem. So the polynomial takes an n squared matrix and an input y, which is the characteristic vector of the click to be planted, and the output is this constant degree polynomial. Like at the coordinate ij, you take the OR of yi yj and the xij. And the parameters, the polynomial here is specified by the parameters of what is this product distribution. So x will will come from a p-bias distribution, or so it'll come from a p-bias distribution, and we'll think of p as maybe n to the minus delta. So n is something that changes, but delta would just be a number. And similarly for the y. So we would only kind of want to some maybe gamma.
So I think in all of these examples, the u1 through ur are also just generated randomly, right?
Yes. Yeah, all of these examples basically. First of all of these examples, these are product.
So maybe these are Gaussian with some.
Gaussian, yes.
And they are not parameters really.
Yeah,
Yes, I don't know. So all of these examples, the inputs here are just product. All of these examples, the inputs come from a product distribution. So the parameters are really the parameters to specify the product distribution and what you do with it. And what is the cleanest way to say, to capture all of them? Maybe I have to now think about whether this, invariance is enough to fix the number of polynomials to only a constant, or maybe you write and it's not. And then I need to like have an extra requirement. But generally, the idea would be that you specify that all of these distributions at least look like basically very structured polynomials that only take a product distribution as inputs, and they are low degree. And for some of these definition of Boolean equivalence, you can show that these things are like miss those things, but it's actually can be it can be more challenging to define exactly what is all possible of things that preserve this kind of symmetry, etc. And since you kind of want,
can you go back one slash?
Yes.
What
the last
statement? So what? How do you rule out that? How do you rule out this particular?
So, for example, if you can show that, say, a random degree D graph for every D, there will never be a small number of graphs such that such that with high probability you are covered. You are up to a permutation. You are close to one of those graphs. Within small Hamming distance. So for some simple, if you define kind of simple definition of just say permutation and noise, but you can prove that these simple models do bypass those obstacles. It's not so easy if you try to think of what is the most general, and think of what is the most general thing is this kind of more radical definition. And then it might not be so easy to even prove that these things bypass all these obstacles, and that's also like something that will need to be done. So let me, and then these things will kind of imply you'll get hardness of these, like I said, these all sorts of average case problems that kind of fall under this model. So that part will work. And now this more radical definition, let me kind of say, basically the idea is that you want to say that you want to say that you're good unless there is like an obstacle. And what will be an obstacle? Basically, the idea of an obstacle would be the following. You'd say that instead of asking that if then your algorithm succeeds, you'd think of your algorithm, your proof system as being able to reach to talk about more complicated statements. And in particular, statements that talk about implications, that if the value of I prime is at least, say, tau plus epsilon, then the value of I is at least tau minus epsilon. And then basically what you would want to say is that...
Assuming that they have the same function value.
Assuming, let's just say assuming assuming this statement is actually true. Let's just say, assuming this statement is actually true, then you would want your proof system to be able to do these implications. And the idea would be that there is kind of a small list. There is a small list, so that basically for every I there is f of I. You think of it as the index of f in the list. The list element that corresponds to the list element that kind of corresponds to I. And in between two people that kind of come from the same list, you can they are certifiably, the value is certifiably close to each other. So, okay, so maybe the way I would, let's see if did I try, no, let's, I didn't, like maybe the way to think about it is the following. So what I'm trying to say is that the only reason why something would fail is there is a small list, and small might mean here 2 to the n to the 0.99, when it's like the ETH, like n is the number of solutions, the length of solutions, not the length of the instance. And the idea is that you take a ball around all of those, and you define this notion of distance. You say that, say, I is close to I prime if two things are true. Both the actual value of the objective function is close to each other, but also you can certify that this is the case. So there is a small certificate that there is a small efficiently checkable certificate that this is the case, that I and I prime are close. And what you want to say is that a distribution is good if it cannot be covered by any number of these small lists. And that's attempts to capture not just permutations in graphs, etc., but everything that's somehow demonstratably maintains the objective value. And let me just be.
This is similar, somewhat similar to these definitions about robust instances.
Yes, but here I want to kind of capture all classes of perturbation that usually in robust instances maybe they say they only allow modifying epsilon fraction of the edges, but they don't necessarily talk about applying a permutation. But here I want to say I want to capture everything that certifiably doesn't change the objective value.
Yeah, but if the algorithm, the canonical algorithm, has a property that it
yes.
is invariant to permutation, then it will.
Yes. Yes, so you kind of want to say that these distributions don't count. Like if you only count distributions basically on a good distribution is one that misses you define these kind of equivalence classes and also measure of distance. So measure of equivalence and distance based on the canonical algorithm, and then a good distribution is one that is not covered by a small number of these equivalence classes. And okay, so now talking about concrete candidates, so you can think of these search problems, these refutation problems, sampling problems, or an upper bound for entropies. And for search, there are lots of different optimal algorithms you can think of, or candidate algorithms. And the hope is actually that many of those kind of give the same answer, or like you can find one that dominates all the others. And you can think of like things that basically you apply a low degree polynomial to the coefficients of your own polynomial. And maybe after that, you kind of truncate or take the signs or something like that. And this is like these approximate method passing or SDPs, all these gradient descents. And for refutation, this is really proof systems. And for sampling, people have used MCMCs, and also many search algorithms also use that. And
so wait, these are concrete candidates for what?
For being these kind of so for both. One of them might be kind of the optimal algorithm, and when others could be things you want to test against it.
So we are back to defining the complexity measure.
Right, we want to define a complexity measure. I still haven't defined it, and I don't even know the right way to define it. I think for refutation, it's kind of natural, at least for me, to try to use SOS. But you would want to kind of connect it and to show that when you say add noise, even other proof systems that are even not automatizable are not more powerful. But for search, it's also not super clear what's the right way to define. The way Hopkins defined it is using low degree polynomials in the input instance. For samplings, it's also not clear. And for if you want upper bounds, it seems that what you really want to do, and this is kind of something that Pravesh had been in some works doing, is you want to kind of extend SOS to try to prove statements that have more than one quantifier, like for all exist for all kind of statements. And there have been recently some works doing that in the context of robust learning, where they want to try to prove these kind of statements using, so they kind of extend in some sense SOS. They think of like a meta SOS. And this particular might be useful for these kind of notions of equivalence class. So my sense is that maybe the right way to think about it is to have this kind of SOS++ system, which is the richest thing that kind of prove these kind of statements, and then imply from that all of the other things and say this is the optimal thing, and try to show that this embeds all of these other algorithms. But this is still very much, so this is still very much. And a system like that might be able to also useful when you want to, say, prove relations between two exponential sums. You want to kind of show that you can charge the elements in one sum to the elements in the other sum. And right, so this was really more about like trying to get people interested in thinking about this and attacking this in all sorts of ways and showing these kind of results. So we really want to show that these predictions kind of coincide for different algorithms, that when we test, at least with these families of concrete algorithms, we test against each other. We want to use the derive kind of parameters. And in some sense, this is work that has already been done. Like there are all sorts of works that have already been doing this, giving algorithms or lower bounds for concrete algorithms or concrete problems. And like to kind of maybe say that this could be in this framework, and hopefully we'd kind of be able to nail down this right definition. And there is a sense in which I think maybe even for problems like worst case approximation ratio, it might be the case that if you look at it in the right way, this kind of theory might be even cleaner in some sense. It might be that sometimes looking at the approximation factor makes some problems weird, while the picture becomes cleaner. Maybe, for example, unique games might be easy on all good distributions. And you could say, you know, the reason this is kind of like in this gray line between the true and false is that we're just not looking at it in the right way. And in the right way, there would be some part of it which is hard, and part of it which is easy, and in some sense. But yeah, anyway. I just hope it gets you thinking about these kind of things.